Okay, welcome everyone. I see that there are a good number of you here. It looks like 165 people. So we have still probably 3 minutes before the start time of the class. So I'll use those 3 minutes to let you guys ask questions if you like. You can ask questions over YouTube chat, and then we'll get started. Okay. Still echoing? My day is going great, thank you. Okay, good. So in case you're wondering why I'm using YouTube instead of Zoom or something else, platforms like Zoom and Google Meets, they're great for face-to-face meetings where you're staring at someone's head, but it's extremely hard to get them to do any kind of high-resolution video. So something like a whiteboard like this just doesn't show up on either of those platforms. And that's true whether you've bought a pro account or not. It seems like YouTube is really the most reliable streaming platform for the kind of stuff that we want to do, where you have one person lecturing and many people watching. Assignments are not best 3 out of 4. Assignments are what they are. So they're as you see here, worth 75%. All of them will be counted. There may be 4, there may be 5 assignments. We'll see how things progress. So as for videos, these YouTube broadcasts that we do, they will be available basically immediately to watch as a replay after the lecture. In addition to these YouTube broadcasts, there's another camera in this room that's recording me. And that camera that's recording me is a little bit better than this webcam that's doing this broadcast. So the recording from that will be posted online, hopefully within 24 hours after a lecture. But I just saw that the hour and 20-minute lecture turns into an 11 gig file. So it may take a little while for me to get that uploaded from my home internet connection. It's definitely something that's going to have to happen in the evenings after people have stopped using the internet. Okay. So anyone have any further questions for me? There's approximately a 3-second delay between the time I speak and the time YouTube gets it back to you guys and back to me on the tablet that I'm looking at. So when I pause to ask if you have questions, I'll often wait what seems like an awkward amount of time, but that's just because I need to give a little bit of time for you guys to catch up. Yeah. So as you've noticed, and another reason for recording the lectures using a different camera, whiteboard is blurry at the edges. That's just a artifact of using a webcam to do this. Webcams tend to be optimized for close-up shots, and so the webcam is fairly close. It's further from the edges of the board than it is from the center. All right, so welcome everybody, for those of you who just showed up. Today we're going to have a little introduction to the course, go over the course outline, and I'll also introduce to you the stuff that we'll need to get into fairly quickly so that you can get started on the first assignment. And that's the introduction to the parts of the Java collections framework. So without further ado, here we are. So this is me, Pat Morin. I'm a professor in the School of Computer Science. I've been there quite a while. If you need to address me somehow, if you need to talk to me, please just use my first name. I'm very happy to be called Pat by anyone. I don't need any titles or anything. If you're not comfortable with that, then just don't call me anything. There's lots of ways to get my attention without calling me by name. Hopefully you're here for the right course, COMP2402. I believe it's called Abstract Data Types and Algorithms or something like that. That's the official name. I just call it data structures because that's really what the course is about. Here's the link to the web page for the course, but presumably if you're here watching on YouTube, you've already found that, because I don't know really of any other way to find this video. This will be the web page to go for the YouTube links for the live streams that we do for the classes. So feel free to go there, as well the links to the recorded classes to rewatch or to watch for the first time if you missed the live stream. They'll be there. The grading scheme for the course, some of you have noted already, it's assignment heavy. There's a couple of reasons for this. One of them has to do with the fact that we're going to be fully online this semester. It's very hard to maintain integrity of exams, but another reason is just that this grading scheme probably is a better representation of the amount of efforts that you have to put into different parts of the course. Exams, right, they typically, you study for a few days or a week for them, and they're typically worth tons, whereas assignments, you spend the entire semester doing assignments, working hard on them, and they're usually worth less. This grading scheme represents somehow something that's more related to the amount of effort that you put in. So assignments will be worth 75%. There'll be 4 or 5 of them. Talk a little bit about those in a minute. And the textbook for the course is Open Data Structures. It's free on the course. You can get it from the course webpage. You can get it from the book's website. And if you need review material for some of the background, and the background for this course would be COMP1805 is probably your best bet, as well as introductory Java programming, wherever you got that from. There are links to, well, there's a link to a free discrete math textbook as well on the webpage. So there's nothing to buy for this course. If you have a computer and you can install a Java development environment, which presumably you've done already, then you're all set. Okay. Any questions? Okay, do you have to pass the exam to pass the course? No, you have to get a grade greater than 50% to pass the course using this grading scheme. Okay, so it seems we have some visitors here from YouTube. I guess this morning's lecture that I gave on discrete math was fairly popular, and now YouTube is recommending it to random people. So welcome if you just dropped in. This is a university course on data structures. If it's not of interest to you, feel free to leave. If it is of interest, feel free to hang out, but don't clog up the chat room with talk, because it's the chat is the method that I'm using to communicate with students, to take questions from students. Okay, so one thing that we should mention is about these assignments. This will probably be your first experience with this, unless you took this course before. Hopefully that's not the case. The assignments will be graded by an automatic submission server. So typically an assignment contains, well, there's the text of the assignment that tells you what you have to do, but there's also a sort of bunch of skeleton files that you do things in. So there'll be some Java files provided with function implementations missing. Your job will be to implement those things. And when you do that, you answer the questions on the assignment. You take all those Java files, you zip them up in a very specific way. You log into the submission server, upload that zip file. The submission server will unpack those things. It will compile them, and it will run them and test them. And what you get back from that is a grade. So your grade for that assignment. This whole process happens in 30 or 40 seconds, and which is nice. You get to know instantly how you did. But what's really nice is that's not the end of the story necessarily for you. If you're unhappy with how you did and you still have time before the deadline, you can revise your assignment, try and fix things, and resubmit, and see if you do better. This submission server keeps track of all submissions that you make, and when we compile the grades for an assignment, you will receive the best of the grades that you submitted. So if it's approaching the deadline and you've submitted and you've got a grade of something like 80% and you think you can do better, feel free to try to do so. If you accidentally muck up your code and your grade drops to 50%, the grade of 80% will still count. Okay, so in that sense, there's no drawback to submitting frequently. Although if you do muck up your code, it's good to do something like revision control, or at least keeping backups, so that you can go back to a better version of your code in case you want to keep trying. So those are some of the advantages. You learn how you did right away. As soon as you get 100%, you can stop. Or as soon as you get a grade that you're satisfied with, you can stop, and you can submit as often as you want. That's the good news. The bad news is that the submission server is necessarily rather picky about what it accepts. For instance, the reason that you get some skeleton code and files with very specific names, and they're in very specific packages, is in order for this testing to happen, everything has to be exactly right. So if you do something like change the package that the file is contained in, or that a class is contained in, then the submission server won't be able to compile it, so it'll fail during compilation. And when that happens, you get a grade of 0. There's nothing else we can really do with a submission that doesn't compile other than give a grade of 0. And so that's something to keep in mind when you're working on this. And many of you are used to using integrated development environments that have their own ways of laying things out, or at least they have ways of laying things out that you're used to. And so one thing that happens frequently in this course is someone takes their assignment skeleton because there's a package directive in these files. It doesn't quite work with their integrated development environment. And so rather than learn how to make it work with their IDE, they just comment out the package directive, work on their assignment, get it all working, think that everything's working great, and then they submit it to the submission server. It doesn't compile and they get a 0. Students are generally angry when this happens, especially if they wait until very close to the deadline. So don't do that. If the files that we give you, the example files, they compile if your development environment is set up correctly. They compile just fine as they are. If you have to comment things out or change things to get them to compile, then you're going to have a problem. Then it's just not going to compile on the server. Okay. Any questions about that? Is there a recommended IDE? No, in fact, just the opposite. I recommend a good text editor and the Java compiler and Java runtime environment on the command line. Once you understand, if you can do this from the command line, then you understand, for instance, how directory structure mirrors package structure in Java. There's no IDE hiding things from you or slipping in arguments that you weren't aware of. And ultimately, the server is a headless server. It's doing exactly that. It's compiling with command line compiler and running with interpreter, a Java interpreter from the command line. Yeah. Okay. Good. All right. So now for a bit of a motivational spiel. Usually I have sort of fancy slides for this, but it's a bit hard to mix slides and whiteboard. So I sort of copied about the contents, the rough contents of 10 slides onto the whiteboard before you arrived. And so what I'd like to sort of motivate is the 5 W's of data structures, what they are, why we use them, why we study them, how, who does it, and when this happens. So first we'll start with the what. What is a data structure? Well, it's something lives inside a computer and it stores data. Okay, so that's one aspect of a data structure is it stores data, and generally somehow large amounts of data. So when we talk about data structures, there's usually this variable n that we're using, and n invariably refers to the number of pieces of data stored in the data structure. So what kinds of things store data? Well, for example, disks store data, but they're not by themselves exactly data structures. The other aspect of data structures is not only do they store data, but they can do things with it. So you can ask questions about the data, queries about the data, and these data structures will answer those queries. They'll tell you, they give you some access to the data. It's not that So a hard drive full of data that's locked up inside a vault that you can never get to doesn't qualify as a data structure, because although it's storing data, it's not able to give you any useful information about that. So data structures should be able to answer questions about the data. And maybe, and a lot of the data structures that we'll see will allow updates of the data. So maybe you can add data items or remove data items or modify data items that are stored in the structure. So that's about the vaguest definition of a data structure that I can come up with. But ultimately, those are the common elements of data structures. Why would we want to use data structures, or why would we want to study data structures? Well, it turns out they're really important. Pretty much every part of a computer system has non-trivial data structures in it. So, for instance, for your computer, your desktop computer to run, or even your phone computer, you're underlying that thing that lives there, there's a file system. Okay, what's a file system? Well, it's a giant collection of files that contain data. And your file system can answer queries about that data. It's not just a bunch of flat bits laid out on some hard disk or on some solid state drive. There's a whole directory structure. You can ask to list the contents of a directory. That's a query. You can ask for the contents of a file off the disk. So ask for some of the bytes in a file off the disk. In fact, you can ask for a specific block in the file. And these data structures store, I mean, disks are huge nowadays, right? We're talking terabytes. So that's I mean, that's a 1 with 12 zeros after it. So huge amounts of data, and yet you can still access any file on that disk at any time very, very quickly. So that doesn't happen for free. There's a lot of hard work in the data structures that manage file systems to make this possible. And you can imagine that navigating terabytes of data is not a trivial thing. And already this has to happen just for your computer to store its operating system and boot up. Search engines are another big example. If you go to Google and do a search, remember Google indexes the entire worldwide web, which I don't even know what the estimates are currently on the amount of data or even the number of active URLs on the web right now. But in a fraction of a second, Google can find any of those things that contain the search terms you're interested in. So you can imagine that, again, there must be something fancy going on under the hood, because this is huge, huge amounts of data, much bigger than is on a disk. When you ask Google a query, it's not that they have a really fast network connection and they go around searching the entire web for the keywords in your query every time you make a query. No, they've actually gathered up the contents of the web, compressed them down, and stored them in a way that makes it very fast for them to find web pages that contain certain keywords, and even better, to find relevant web pages, so the ones that are likely to be most important for you. And another example is video games, or if you don't like video games, simulations of the real world. So the video games sort of have a couple of components. There's the graphics component, a lot of which is handled by the graphics card these days. But there's also a whole physics component. Graphics cards can help with that, but part of the physics component is things like collision detection. So that's what allows you to make a video game where a player cannot walk through a wall, or when a bullet is shot, that bullet doesn't just pass through a character or through a wall. There's data structures there that do very careful and very precise collision detection. So that bullet hits exactly what it was, the first thing that it would strike. A character can't walk it through a wall. They bump into it, get stopped by it. Vehicles crash into each other. And in large games, and imagine even these sort of massive multiplayer online games, there are many, many characters. In fact, there can be, 1 million users using the game at once. Huge worlds. And somehow the game servers are still able to keep track of when two particular characters run into each other, or when one character runs into a wall. And again, that's not done in a trivial way. So you have to be very efficient if you're going to have things scale to those scales. Make sure that you're only really doing the least amount of work possible to detect all collisions, but also not to miss any collisions. So there's good reasons why we need data structures, why you should be interested in studying them. How do we study data structures? For that, we ask questions. We use a few sort of questions about them. So when I said what a data structure was, I was super vague. Just said it's something that stores data and supports some kinds of operations on that data. So we should be more precise and ask, well, what is this data structure representing? So is it really just a collection of stuff with no particular order and nothing really exciting we can do about it, maybe other than list its elements? Is it a set of things? So is everything in the data structure different, and nothing appears twice or more in the data structure? Or maybe it's a sequence. So sets, if you remember, there's sort of notion of order in a set, but a sequence is really a list of things, one after the other. And so maybe the data structure represents a sequence, or maybe it's a map. And maybe by map, I could mean lots of things. Maybe it's a map of the world, maybe it's a map of your house, or maybe it's what we'll end up calling a map in this course, which is really what other people call a dictionary. Okay. All right. So what does it represent? What operations does it support? Well, sort of standard things are maybe you can add items to the data structure or remove items from the data structure. Maybe you can search for things in the data structure. So you can ask, where is X in this data structure, or is X in this data structure? Maybe what comes before X, what comes after X, those kinds of things. Or maybe you can just access things. For instance, you say, well, what is the 100th thing in this data structure? So what does it represent? And then what operations does this thing support? And of course, the operations may or may not make sense depending on what it represents. For instance, in a sequence, it makes sense to ask for the 100th item in the sequence. In a set, that doesn't make sense because items have no particular order associated with them. So if I ask for the 100th item, could be anything. So there's these two questions. And then finally, there's the question of performance. What kind of performance does your data structure have? And in this course, we will primarily be concerned with speed. So how fast does it support the operations that it supports? How fast is it to access something? How fast is it to add or remove something? In some circumstances, and a little bit in this course, but not too much, you're also concerned about memory. So how much space does your data structure use? If I store 1 million items in the data structure, well, how much memory does that take up? And so that can be an issue too. We'll talk a little bit about that in this course, but mainly we're interested in speed. And the two sort of go hand in hand because if you have a huge data structure, then somewhere it's going to be slow at doing something, because just making a huge data structure takes a long time. So it's kind of nice that these two things sort of help each other. If you want to be fast, you shouldn't require too much memory, because just using that much memory takes a lot of time. These questions that we've asked so far, they sort of naturally fall into two categories. The first two, what is this data structure? Why do we, sorry, no, got that wrong. What does the data structure represent, and what operations does it support? Those are what in this course we will call the interface. So these are not questions about how it's implemented, how it does these things. They're just questions about what it does. So what can I do with this data structure? What questions can I ask it? And what is it supposed to represent? We're adopting the Java terminology. We call those the interface of the data structure. In some more sort of classic branches of computer science, they might call this the abstract data type. And these questions about performance, they are about the implementation of the data structure. So, and we tend to separate these two things. We separate the interface, what kinds of operations are supported, from exactly what the implementation is of those operations. So for implementations, we might talk about things like binary search trees or skip lists or hash tables. For interfaces, we would talk about things like sets, sorted sets, maps, sequences, things like that. So you think of the interface as some black box definition of what you can and can't do to this data structure and what you can expect when you do those things. And the implementation is really under the hood, how it does those things. And you can have different implementations of the same interface. We'll see many examples of that in this course. Okay, so any questions right now? I'll try not to knock my iPad over. It's okay. It's a carpeted floor, so I'm not too worried even if it does fall over. Can you use IntelliJ? Yes. A sort of note about IDEs. On this course, on CU Learn, the course forum is active. Some of you actually want to set up Discord groups for courses. That's fine too. Whatever you do, I recommend that you help each other out with these sort of annoying details of how to get my IDE to deal with the example files that you get for an assignment. So typically, IDEs, and this is another reason that I like the command line, typically there's a really thin interface in an IDE that's just hiding the command line only a little bit. In fact, often if you have to do anything slightly out of the ordinary, what ends up happening is your IDE has a dialog box in which you put in little strings like -q, -v, -xmm, something or other, Well, those are just command line arguments that the IDE ends up passing down to the underlying compiler or the underlying runtime environment. And they can be really hard to find in an IDE. So on a command line tool, you look at the man page, you can see the list of all of the arguments that this thing supports. You can find the one that does what you need it to do. But if you're using an IDE, then you're not done yet, because now you have to navigate the IDE's interface until you can find the place, the dialog box that lets you specify that particular thing. Maybe you can specify it by putting a string in some dialog box, or maybe you have to hunt through 1,000 menu options until you find a checkbox that basically forces that command line argument to get passed to the compiler. And different IDEs hide those things in different places. I don't really use any of them anymore, and there's no way that I could be an expert at all of them. But there's several hundred of you in this class. There's several hundred more in the other section of this course, and so if you have a question about that kind of thing, or if you've solved a problem related to that kind of thing, feel free to post it on the forum and save everybody else a ton of time, or ask the question and save yourself a ton of time, because there's a very good chance someone else has solved it and can answer in 2 seconds. I hope to have the first assignment up within the week. The first assignment will involve using the Java collections framework to do some data processing tasks to make sure you understand the interfaces and understand something about the performance of the implementations that are present in the framework. Yeah, so I hope to have that within a week. Okay. So I will give a short introduction to the interfaces in the Java collections framework. The interface hierarchy is not very big. And remember, when we talk about interfaces, we're just talking about what operations the structure supports and what those operations mean. Not how the structure implements them, not how the data is actually stored, not what the algorithms look like, just really what those operations mean and what you can expect if you, as answers if you do those operations. So at the top of the Java collections framework is one sort of, the hierarchy is split in two, but on the big side of it, there's an interface called collection. It's sort of a catch-all thing that everything that stores data, at least individual pieces of data, ends up being some kind of collection. Collections, you can't really do very much with them. There's not very many interesting things about them. Typically, though, there's 2 operations you can count on, and so I'll just mention them, and then I won't mention that every other thing in the collections framework also supports them. You can ask a collection about its size. So I mentioned already that when we talk about data structures, we almost always talk about some underlying variable n, which is the number of items stored in the data structure. In particular, this comes up when we talk about the running time of various operations. There's often a function of n, or even the memory requirements, which is also a function of n. So when you ask a collection for its size, it's basically going to tell you the value of n. How many things are stored in the data structure? And the other thing you can count on a collection for is iteration. And that means you can write for loops for collections. So you can say for object O in some collection C. And this is a for loop in which O will take on the value of each of the n objects in the collection one time through the loop. So you can iterate over collections using a for loop like this. It's a common thing, and it's handy that every collection supports this because there's lots of sort of easy operations you want to do where all you need to do is look at everything in the data structure in order to do that thing. Maybe it's not very efficient, but it's an easy way to do it, and sometimes it's necessary. So collection is not terribly exciting. But under collection, there's a pile of things. We have set. We have list. Queue. And deck. And under set, we have a special kind of set, which is a sorted set. Okay. That's part of the hierarchy, or that's the large side of it. And completely separate from that, there are two more classes, map and sorted map. Now, these names were chosen by the designers of the framework a long time ago. They're reasonably decent names, but sometimes they lead to confusion because in other contexts, sometimes these names mean quite different things. In particular, some people think of lists as a particular implementation. That's not the case in the Java Collections framework. It's really just an interface, tells you what operations are supported. And some people think of queues as a very particular kind of thing that represents queues like, we think of queues like lineups where people stand in line. There's someone at the front of the line. There's someone at the end of the line. These queues are more general than that, and we'll see in a few minutes what we mean by that. Okay. Sorted map is under map, yes. So totally off in a different hierarchy. There's map and sorted map. All right. So what about this set here? So we've seen collection. It's kind of boring. You can ask its size and you can iterate over it. What about set? Well, set, this is a good name, I think, because it really represents the mathematical definition of a set. If you have taken a discrete math course, you go back to remember what you learned in 1805. A set is an unordered collection of distinct elements. Okay, so there's two important words here. Unordered, meaning that you can't rely on them being in a certain order. And in particular, if you use a for loop on a set, which you're allowed to do because a set is a collection and every collection lets you iterate over it, you cannot rely on the order in which the elements come out of the set. So if you put a bunch of numbers into a set, don't rely on them coming out in increasing order. Don't rely on them coming out in the same order that you put them in on. If you, in extreme cases, you can't even rely on them coming out in the same order if you iterate over them twice. In particular, if you did some operation which looks like it shouldn't have changed the set, like you add something and then remove it, then maybe before you did that, you iterate over the set, the elements come out in some order, you add an element, remove that element, iterate again, and they come out in a different order. That can easily happen. And so you can't rely on order within a set. And the other sort of keyword here is distinct, meaning that no element appears more than once in the set. Okay. So sets support basically 3 operations, which are, I can take an element X and add it to the set. If I know that an element X is in the set, then I can remove it from the set. And if I'm not sure if an element X is in the set, I can ask, is X contained in the set? So does the set contain X? Okay, so this is obvious. X, you put it in the set. Remember, you can't put the same thing in twice. If you try, either nothing will happen or you'll get an exception. If something is in the set, you know it's there, you can remove it. And if you're not sure if something is in the set, you can ask if the set contains it. This returns true or false, depending on whether or not X is in the set. And so you often see an if statement that has a contains X as the condition and maybe a remove X in the body. So you don't try and remove something that's not in the set. So these are the 3 important operations on sets. And if you use sets and you stick to these operations and possibly iteration, then any good implementation of a set will be able to do these things very, very quickly. And we'll see the kinds of techniques that are used for that. But good implementations can do all of these things in a size that is independent of the number of elements in the set. So it doesn't matter if your set contains 20 elements. It doesn't matter if your set contains 1 billion elements. These operations should run at the same speed in both cases. And that means fast, of course. Do you need to memorize the graph for the hierarchy? No, I don't think you need to memorize the graph, but you'll end up working with these things already in the first assignment. So it'll kind of just grow on you. Plus, it's not a particularly complicated hierarchy and kind of makes sense, right? Set and sorted set, for instance, it's not hard to remember that, well, a sorted set is just a special kind of set. And inheritance hierarchies, that's the way these things work, right? The child is a special kind of thing of the parent. And a collection, well, that's a pretty generic term. So all of these things are just a special kind of collection. Other than that, there's not really much to remember. Okay, so that's set. sorted set it's a special kind of set, so it supports adding, removing, and contains, but the let's say it's a set in which the elements are stored in sorted order. Okay. What does sorted order mean? Well, all of the basic data types in Java have a natural sorted order associated with them. Strings, for example, work with the lexicographic comparison. So in Java, you can ask if one string is less than or greater than another string, and it just does alphabetic lexicographic comparison. Integers and real numbers, of course, they just get compared the obvious way. So they get sorted in increasing order. So a sorted set, if you store these kinds of natural data items in them, then they'll get stored in that natural sorted order. If you want some special kind of order, maybe you want to reverse the natural order, or you want to do something like with strings, you want to do case insensitive comparisons, so that doesn't matter if letters are uppercase or lowercase. You can override that, but if you don't, then you just get the order that you would expect. And so what effect does this have? So that they don't have this unordered property anymore. They're somehow in sorted order now. So that means iteration works in sorted order. So if I have a set that contains 1, 3, 5, 7, 8, so a real set, and I iterate over that thing, these numbers will come out, and so I make a for loop for that set. The objects numbers will appear in the for loop in some order that's probably not sorted order. But if I do this in a sorted set and I run a for loop over this, then I will see 1 will be the first value, 3, then 5, then 7, then 8. Okay. So that's handy. You can add things, you can remove things, and you can ask if they can contain things, just like you can with a set. But there's also some additional operations. You can ask for the first thing. So first here means the smallest thing, or if I was to iterate, what is the first element that would appear inside my for loop? So it gives you the smallest thing in the set. So we'll call that the smallest item in the set. Well, if you can ask for the first, then it also makes sense that you could ask for the last. That gives you the largest item in the set. And so that's good. It lets you, if I ask for the first in this set, the answer will be 1. If I ask for the last, the answer will be 8. There's first. There's last. But you can also get what are called views of sets. And I can ask for the head set. And that takes an argument x, and it will give me, or it returns, set containing everything smaller than x. So here, for example, in this particular set, if I ask for the head set of a 4, what I'll get back is a set that contains 1 and 3. Everything smaller than 4. If I ask for the head set of 7, I would get a set that contains 1, 3, and 5. Everything smaller than 7. Okay. And I will, when we look at implementations, we'll see somehow why this matters. But it's kind of important to remember that this head set is really, it's not a completely different data structure from the original set. So you get back something that looks like a sorted set that contains, for instance, in this case, only the elements 1 and 3. But really what's happening is there's an underlying larger set, the original set, that contains all of these things. And the object that you get back from headset is using that, but it's only letting you see the things that are smaller than 4. In particular, if you ask for a headset and then you try to do things to it, add things or remove things from it, then that may cause a problem, because the only thing it can do in that case is to add or remove things from the original set, which somebody else might still be using. And depending on the implementation, you may get that simply may not be allowed, or it may cause unexpected results. Okay. And of course, if you can ask for a head set, well, you can also ask for a tail set. And a tail set does sort of the inverse of head set. It gives you all of the things that are greater than or equal to x. So for example, if I was to say tail set of 5 here for this particular set, I would get a set that contains, or a view of a set that contains 5, 7, and 8. So you can ask for all of the stuff smaller than the particular value x, or all of the stuff greater than or equal to a particular value x. And then there's a unnecessary function called subset that takes 2 arguments, x and y, and it gives you a set that contains everything that is greater than or equal to x, but smaller than y. So a subset you can implement using head set and tail set. You can take a head set of a tail set or a tail set of a head set. Okay. Any questions about these sorted sets? So there's questions about when you return things, do you modify them, or is it immutable? Again, we're talking now about interfaces, and some of those questions then are really questions about implementations. So the thing that I mean, exactly how a sorted set goes about implementing these operations, well, that's a question of the implementation that's separate from what operations are supported. Although the specification may tell you that tail sets and head sets are immutable, or it may just tell you that it's dangerous to modify them. Okay. All right, so that's set and sorted set. And you might ask, well, it looks like a sorted set is just better than a set, because it's not only does it let you do all of the things that a set can do, but it lets you also keep things in sorted order and get these range query operations like head set and tail set, and subset, and first and last. And when you iterate, things come out in sorted order. Why would you ever want to use a set? Well, you'd want to use a set if these are the only operations you need: add, remove, and contains. If you only need those, then you might as well use a set, because as you may be able to guess, it's easier and faster to implement a set that only supports these three operations than it is to implement a whole sorted set that supports these things. In fact, we'll see that implementations of sets, although there's some really interesting math that underlies them, and it requires some number theory to prove that these things run super fast. The algorithms themselves are super simple, just a few lines of code for add and remove and contains. Whereas sorted sets, we'll spend a good chunk of this course looking at data structures that implement sorted sets. We'll look at binary search trees, several different kinds of binary search trees, skip lists. We may look at B trees, which implement sorted sets in another way. So these things end up being more complicated, and because they're more complicated, well, they're slower. So that's why you would choose a set if that's really all you need over a sorted set. And indeed, there's many examples where really order doesn't matter, right? If you think of some database that's keyed by something like social insurance numbers, so that 9-digit identifier that you put on your tax forms, does that really mean anything? I mean, it seems to have nothing to really do with anything. It doesn't make sense to take a group of people and sort them by their social insurance number. It doesn't give you anything meaningful about that group of people. And so if that's really the key that you're interested in, then you might as well store those in a set. Student numbers is another example. Student numbers, they actually, at Carleton at least, they tell you something about how recently the student entered the Carleton system, but usually that's not a very relevant piece of information. For instance, when I'm assigning grades, I don't go easier on the people with large student numbers than I do on the people with small student numbers. In fact, I don't care what people's student numbers are. I don't look at them. Okay. All right. So that's sets, which they are, sets are unordered, and sorted sets are sorted, but otherwise unordered, meaning that the order associated with them is the sorted order. It has nothing to do with the operations that you performed on the sorted set to get it where it was. In a sorted set, if you add a bunch of elements, it doesn't matter what order you add them in. When you iterate, they'll come out in sorted order. And in a set, if you add a bunch of elements, doesn't matter what order you added them in, you can't rely on the order that they'll come out when you iterate over them. So that brings us to something totally different, which is lists. So a list represents a sequence of elements. And those sequence are indexed by integers 0, 1, 2, up to n minus 1. Or if you don't like n, or if you've forgotten what n means, that's the size of the list. So this is almost completely the opposite of sets. There's a specific order assigned to these things, and there's nothing in here about things having to be distinct. So for example, I can have a list that contains A, B, X, A, C, D, A, X, Y. Its elements are indexed by integers. So it makes sense for me to say, what is item 0 in the list? It's A. What is item 3 in the list? It's also A. What's item 5 in the list? It's D. So what operations do lists support? Well, in a list, you can get the value at index I. So in this example, if I say get 2, what comes back is X. You can set the value at position I to any value that you, some new value, X, that you want. So here I could say set 4 to K. And what that will do is go to position 4 in the list, erase what's there, and put a K there. I can add an item to the list, and in fact, I can tell you where to add it. I can ask you to add item X at position I. So what does that mean? Well, if I say add at position 5, the value Z, well, that means that after this operation is done, the item at position 5 in the list will be Z, but I'm not asking you to change the value that's there. I'm asking you to add Z. So really what happens is Z gets put in there between K and D, so after position 4, and all of the remaining items in the list from 5 onwards, their index increases. So after adding Z at position 5, that's what the list looks like. So that's kind of a destructive looking operation, because that one addition changes the indices of everything that comes after it. And so there's a sort of common one, which is the a really common thing to do with lists is to only add at the end. So there's a one argument version of add, which doesn't take an index argument. It just takes the value you want to add, and that adds it to the end of the list. And really what that looks like is that's just add position size. So in this case, if I called add T, the size of the list is 10, right? There are 10 elements in this list. They're indexed 0 through 9. So I would add T at position 10. T goes here. And gets index 10. So this is an unnecessary operation because it's implemented. I mean, you can implement it using the existing add I X operation. Okay. Any questions about this? So if you're not here for this class, if you happen to be stumbled across this on YouTube, please refrain from using the chat. If there's continued problems with this, we'll just start making these unlisted videos and accessible through CU Learn. But hopefully that won't be an issue. Can you say something about assignment 1? No, because assignment 1 isn't ready yet. So all I can tell you is that it will be some series of data processing tasks that have you using these interfaces and some of their implementations. Do lists have remove functions? Yes. The list has a remove I function, okay, which makes sense because really the main thing in a list are the indices. The data just happens to be stored at specific indices. So if I want you to remove something, it's really the index that I want you to remove. And this basically does the opposite of the add operation. So if I say something like, in this example, remove 7, then look in the list, look at position 7. There's some value stored there. It's going to disappear. And since it's gone, I mean, that index also disappears. So every index greater than 7 will have to get smaller by 1. So those used to be 8, 9, and 10. Now they become 7, 8, and 9. Okay. And already you may be thinking in terms of implementations, thinking, oh wow, these lists, they sure look a lot like arrays. Arrays are indexed starting at 0, going up to some value. So that seems like the way lists would be implemented. And the thing to keep in mind is actually there are different implementations of lists. Some of them use arrays, which makes them handy for getting and setting. But you see that adding and removing, especially for small values of I, that's not such a nice operation to do on arrays because, well, for instance, here when I removed 7, that really meant that everything that came after 7 would have to move forward in the array. So that's not maybe the most efficient implementation if you're going to be doing those kinds of operations. And we'll discuss array-based implementations of lists, and we'll also discuss other implementations, pointer-based, and some really fancy ones that are good for that can do all of these operations quickly. Okay, so there's a question about sorted sets. If you said head set 1, would it return the empty set? The answer is yes. So remember, we had a sorted set that contained 1, 3, 5, and 7 or something. So if I asked for head set 1, it would return a set containing everything smaller than 1. And in that particular set, there was nothing smaller than 1. So you get back the empty set. But that was discussing about, that was about sorted sets. Here we're talking about lists. Okay. All right. Clear? So lists are almost the polar opposite of sets. Order totally matters. Index, the order you put things in matters. I mean, the person using a list is completely in control of this order of the things in the list. And of course, if you iterate in the usual way using a for loop for object O in the list, you will get the items in order of increasing index, starting with item 0, then item 1, item 2, item 3, and so on. Okay. So that's list done. And I think the last thing that I'll mention today is queue, only to say that a queue is not what you think it is. So a queue basically supports well, let's say 2 operations. Add. So queue is a collection of things. Maybe there's an example of abstract version of a queue. You can add something. So I could add, I don't know, 15, and 15 goes into this collection, some bag. Nothing says I can't add the same thing twice, so I could add 3. 3 will go into the queue. And then a queue has a remove operation. And the thing that distinguishes this from what we've seen so far is the remove operation doesn't take any argument. So when you remove something from the queue, something comes out of the queue and gets returned to you. What is that something? So take something out and return it. And the exact item depends on the queuing discipline. So there are different kinds of queues, and they differ in what's called the queuing discipline, meaning when you remove something, what is it that comes out? The 3 main kinds are FIFO, first in, first out. That is what we normally think of when we think of a queue. There's kind of a lineup of items, like a queue at a grocery store to see the cashier. When you show up and you want to buy your groceries, you don't run to the front of the line in front of everyone else and throw your groceries on the counter. When you add something, it goes at one end. And when you remove something, it comes off the other end. So that's the first in, first out queuing discipline. There's the last in, first out queuing discipline, which another word for it is a stack. And a stack is like a stack of dishes. When you add things, they go on top. And when you want to take something off, it comes off the top. And the third major category of queues is the priority queue. And that's where the smallest thing. So for instance, in this bag here, this queue here, if I were to call remove, then the smallest thing pops out. In this case, one will leave the queue and come out. Doesn't matter what order I added these things in, what always comes out is the smallest thing that's currently in there. Okay, so we're about out of time for today. I can answer any questions people have, if you like, for the next few minutes. And otherwise, thanks for showing up. It's nice to have some people here. In fact, considerably more people watching this video than there are enrolled in the class. So if you have any questions, type them here. If you're storing objects, how are smallest and biggest and comparisons implemented? In Java, the particular function is compare to. So every Java object or Java classes implement a compare to method, which you say x.compare to y will tell you if x is bigger than or equal to y, or we'll throw an exception if it doesn't make sense to compare x and y. That's the default way things are compared. And if you want to override that, there's a thing called the comparator interface, which defines a function that takes two arguments and tells you whether one is bigger than the other. You write your own implementation of that that does comparisons the way you like, and you can pass it into things like sorted set so that they do what you want. Do any of the interfaces have a find or contains C? So the something that I didn't tell you because I don't want you to ever use it is actually collection has a contains method that will tell you if some object X is in the collection. Now, why don't I tell you about it and why don't I want you to use it? Because if you look at the way that that method is implemented, you'll see that it's just a for loop. It iterates over the entire collection until it finds the object that you're looking for, or it doesn't find it, in which case it returns false. So that's not a good implementation, because it means if you have a billion elements in your collection, looking for one thing, we'll have to look through a billion things to determine that it's not there. So if you find yourself using the contains method on anything other than a set or a sorted set, you're probably making a mistake. You're probably doing something wrong. Rethink the data structure that you're using, or use a combination of more than one data structure if you find yourself doing that. Does headset and tailset return a new list object? Well, headset and tailset are for sorted sets, so they return objects that look like sorted sets. They're more precisely, they are a view into a smaller view into a larger sorted set. On the marking server, when submitting assignments, will it tell us which test cases we got wrong? It will write information about roughly what is being tested. So it might say something like performing add and remove at 100 random locations, and maybe then your code crashes, and it'll say, okay, I mean, you'll see that your code stopped right after it said it was about to do that test. So you'll know that your code failed when adding and removing at 100 different locations. Now, you won't get the exact test code from the server because that would be too easy. It's up to you guys to debug your own code and test your own code, but you get a broad sort of view of how your code is failing on what kind of tests, and then you have to figure out how to test that yourself and how to debug it. Tail set will return a set that contains everything larger or equal to X. That's correct. Assignment 1 should be out within a week. Are circular cues part of the course syllabus? Yes. Can we use a text editor, or do we need to use an IDE? I would recommend that you use a text editor because you'll learn a lot more. Do I give sample outputs for assignments? No, in some cases, I will give implementations of the same data structure that are correct but slow. And so, and your job is to implement a correct but fast data structure. So at least then you'll be able to compare whatever you're doing to know if it's being correct, but you'll still have to make it fast. What is a stack? A stack is a queue in which everything is added and removed from the same end. So it's a sequence of things that you can add or remove at one end. It's usually called the top of the stack. You submit your code as a collection of zip Java classes. All right, so Minecraft gaming dude is kind of an annoying person, so I think we'll call it a class for the day. Goodbye, Minecraft gaming dude.